Welcome to Maths with EJD. In this video, I'll be talking about polar form of complex numbers as the fourth video under complex numbers. Polar form of complex numbers. Okay, so um, here we'll be looking at introduction to polar forms. Then we'll talk about conversion from rectangular to polar forms. Then we'll talk about graphical representation of polar forms, and then we reach a cute conclusion, and then we have some practice questions. Okay, let's delve into that. Okay, introduction to polar forms. Basically, we need to differentiate between rectangular and polar forms for now. So complex numbers, of course, can be represented in various forms. And one of the most important forms is the polar form. Of course, the form we are familiar with that we've been using so far is called the rectangular form. That is that form where you have z equals a plus bi, where a and b are real, a is real, and b, where a and b are real numbers representing the real and imaginary parts of z respectively. So you know a is always that real part, b is the imaginary part, while I is the imaginary unit, and that's the very essence of complex numbers. But apart from this rectangular form, we have found the polar form to be very useful you are going to see later. It is very useful for performing some kind of multiplication without stress. Okay, so the polar form is written as z equals r cos theta plus I sin theta, where r is the magnitude or modulus of z and theta is the argument or angle of z, right? Now, that doesn't just come about uh, accidentally. It still follows from this, as you're going to see very soon. It still follows from the rectangular form, as we are going to see pretty soon. Now, right here, we have that. How do you convert from rectangular to polar forms? So just imagine that you have the usual rectangular form this way. This is the real part, and this is the imaginary part. This is the imaginary part. And then usually, let's say you have maybe you have the real part is A and the imaginary part is B. So, the point Z, so to speak, is somewhere around here, right? That is this meeting with this. So this is your point Z, right? Then you draw a line here to meet that, to represent the complex number. But this is that point A comma B, So this is A plus BI. I mean, this line is A plus BI. Now, having this, you can already see that this, of course, this is coordinate A comma B. If you are going to do it on the real imaginary side, that's A comma B. And then this, so if you imagine that this is R, that magnitude, right? Because you've been told already that R is the magnitude from the previous place. And then we have the argument. That is like this angle here, which is like theta. Okay. Now see what happens. You already know that from here to here now, all of this can be seen as A. This whole length is A, and this whole thing is B. Starting from the origin up there, this is B. So, and already, so this is like this is like a right angle triangle. So from here already, you can see that R squared is equal to A squared plus B squared, because this is a right angled triangle. So the square of the hypotenuse R is equal to the square of A and plus the square of B. So that's why R squared is equal to A squared plus B squared. And that is why R can now be square root of A squared plus B squared. So you see the R squared you have here is not accidental. The square root of A squared plus B squared. Now, how do we take care of the angle? Now you can see the angle is here. So that's theta, right? And the opposite is B, and the adjacent is A. And to combine opposite B and adjacent A, what you need is tan opposite over adjacent. So you have tan theta equals opposite B over adjacent A, so that theta itself is the arctan or the inverse tan of B over A. And that is why you have this. So you can see it is not accidental. So by the time you're done doing all that, then you can represent, of course, we can actually resolve. We can resolve R according along A and B. Okay, I guess that is also important to do that part. Let me show you the way to go about that. So you see this R now, you can resolve it horizontally and vertically. So to resolve it horizontally is to look at A, right? Compare A and R. So A is the hypotenuse, R is the hypotenuse, and A is the adjacent, okay? Because the angle here is theta. So this is opposite, this is hypotenuse, and this is adjacent here. So if you put A and R together, so that's adjacent and hypotenuse, you need cosine. So you know that cosine of theta is equal to adjacent A over hypotenuse R, so that A itself, which is the horizontal, is actually R cos theta, because R multiplies theta. So you have R cos theta. And for B, right, B is the opposite and R is the hypotenuse. So in that case, you need sine. So that means that sine of theta is equal to opposite B over hypotenuse R. So B itself is R sine theta. So having resolved this into horizontal and vertical, so your overall Z now can be represented as something like this: REI raised power theta, and the expression is the same thing as R cos theta plus I sine theta. So that means the addition of r cos theta, which is along the real line. So that's why it has no I. But then r sine theta, which is vertical, which is along the imaginary line. That is why you have that joined with an imaginary unit. So Z in polar form is REI theta equals r cos theta plus I sine theta. That is extremely important, right? Now, each of these forms actually have where they are useful. For instance, this is very useful when it comes to multiplication and subtraction, multiplication and division of polar forms. And then this you can find useful in under subtraction and addition, and that is what I'll be considering in the next video. So that's how you convert from rectangular form to polar form. So let's do some practical examples. Here you want to convert from rectangular form to polar form, right? So you want to convert Z1 equals 2 plus 3i. This same Zi we'll be using from the very first video, I believe. So Z1 equals 2 plus 3i to polar form. So in that case, your A is 2, the real form, the real part, and B is 3, the imaginary part. Such that to get the magnitude R, now it is simply square root of A squared plus B squared. And A is 2, so you have 2 squared plus 3 squared. 2 squared is 4, 3 squared is 9. So 4 plus 9 is 13. So your magnitude is square root of R13. And in decimal form, it's 3.61. And to get the argument or the angle, right, that's arctan of B over A. So that's arctan of 3 over 2. And in degrees, that is 56.31. Then all you need to do now is to put it in this form, RE raised power I theta. So R is 3.61, E raised power I, theta is 56.31 degrees. And then you can also put it in this form, which is exactly the same as this. So here now, you have that as 3.61 cos 56.31 degrees plus I sine 56.31 degrees. So that's the easy way to go. Just get your A and B. Then once you get your A and B, you just get R, get theta. And if you want to take it back to this form, it's simple, very simple. Just find the cosine of 56.31 multiplied by 3.61. You're going to get something close to 2, if not exactly 2. And then find sine 56.31. It's more like expanding this, right? If you expand this, you have 3.61 cos 56.31 degrees plus I 3.61 sine 56.31 degrees. So if you multiply this out, find the cos and multiply by 3.61, you get that. Then find cos of sine of 56.31 multiplied by 3.61. You get something close to 3, if not exactly 3. And that's how to convert back from polar to rectangular. That's important. You should be able to know how to do the switching. So sometimes some operations are more convenient in polar form, and you have the complex number in rectangular form. So you need to be able to convert that easily. So you can switch between the two and do your operation. And then if you need to convert back, you can always do that. So we have yet another example. So we want to convert Z2, which is 1 minus 2i to polar form. Again here, A is 1 and B is minus 2. Minus 2, the imaginary part. So your R is simply square root of A squared plus B squared. That's square root of 1 squared plus minus 2 squared. That is square root of 1 plus 4. That is square root of 5. And in decimal form, that's 2.24. And then to get the angle, you have theta equals arctan of minus 2, that's b over 1, minus 2 over 1. So that's arctan of minus 2. So minus 2 over 1, that's minus 2, right? So if you get the arctan of this, you're going to get minus 63.43. Now, when we do the graphical representation, you'll understand the implication of this minus 63.43. So it's more like, of course, normally we do angles anti-clockwise. So this is like 0 degrees. This is 90 degrees. This is 360 degrees. And this is, this is 270. No, that should be 180. That is 180. This is 180 degrees. This is 270 degrees. And then 360 degrees coincides with 0 degrees again. So whenever you have this minus 63.43, it means instead of going anti-clockwise, you're actually coming clockwise. So it means the angle is something around here. So it means this is 63.43. So if you still go clockwise, you can go all this way. And that is why the way to get this is to subtract the 63.43 from the whole 360 degrees. So you get this part we need. And that is now your 296.57 degrees. All right. So when you get a negative like that, so it means you're starting from 0 and you're going clockwise. But normally angles are counted, they are measured anti-clockwise, right? So minus means you go clockwise. Then to get the real angle, you go from, maybe I should change the marker to show that part. So it means you now need from here now to this place. But what you originally had was this part. So if you subtract this from 360, then you get what you really need, which is 297.57 degrees. That's really important to note. Okay, so with that now, you have the theta to be 296.57 degrees. So now Z is RE I raised power theta, and that is equal to R cos theta plus I sine theta. All right. So now R is 2.24. So you have 2.24 E raised power I, 296.57 degrees. And you can rewrite that as 2.24 cos 296.57 degrees plus I sine 296.57 degrees. So that's another one right there. So let's talk about the graphical representation of these things you have done just now. It's very good to see the graph of these things. So graphical representation of polar forms, right? The graphical representation of complex numbers is the in the polar form involves using polar coordinates. It involves using polar coordinates. So you have the rectangular coordinates, rectangular coordinates is x, y, That's our rectangular coordinate. Or it is also called the Cartesian coordinate. That's named after René Descartes, the French mathematician. So it's x, y. But when you talk about the polar coordinate, it is r, theta, where r is the magnitude and theta is the argument or the angle. So here you have x and y, two axes, and here you have magnitude and angle, right? So those are the differences. So the angle theta represents the direction and r represents the distance from the origin. And then you can easily see that on this plot. So for the first thing we did, we had 2.33i, which was converted into polar form to be this, which is still the same thing as 3.61 e raised power I, 56.3 degrees. All right. So of course, you've already understood the rectangular form from the previous classes. 2 plus 3, that means on this axis you have 2, which is somewhere around here. So you take that up, and then 3 somewhere around here. This is where that meets. So that's where you have your points. Your points 2 plus your points 2, 3, and then this line you draw that to go, and then you have 2 plus 3, 1. That is in the rectangular coordinate form. But if you go polar, right, that's angle, right? So if you go polar, you see that this is 0.5, 1.0, 1.5, and it goes on and on. So the magnitude of that line, you see that it is actually 3.61. So that's why you see that this last line is 3.5 and this one is 4.0. That's why this dot is between 3.5 and 4.0. So 3.61 is somewhere around there. So that's the line drawn. And then you see, if you look at the angles, right? If you look at the angles, this is 0 degrees, like I showed you before. This is something like 45 degrees. This is 90. So it means this angle 56, this 56.31 degrees is somewhere around here. That's how you draw the polar plot. That's how you draw the polar plot. So For the second one, right, it's exactly the same thing. Okay, so we had 1 minus 2i, and then that translated to 2.24 cos 296.57 degrees plus I sine 296.57 degrees. So again, you see this one now, 1 minus 2i. So it's 1 on the real axis. So you have 1 around here, and it's minus 2. So you see, this is the origin in this case. This is the origin of this graph in this case. So this is the origin 0, 0. So minus 2 is somewhere down here. So we have this. So you have these two lines meeting here, and then you can draw this from the origin to come that way. Okay, so that is it. But then talking about the angle, right? You see the angle. Okay, it's very important to also note this. So look at this. So this that minus 63 point something we got, minus 63 point something we got. This is it here. Minus 63, maybe I think 4.43. It is this angle right here. All right. So this is the line. So this is the angle here. But what we actually need is the other angle that is from here down here. And that is why you get that by subtracting 63.43 from 360 degrees. And that's how you get 296.57. So when you come here to, you see that the magnitude is 2.24. So you see this is 0 0.5, 1.0, 1.5, 2.0, and this is 2.5. So 2.24 is somewhere around here. And then the angle is 296.57. So this is 270, right? So it's so 296.57 is somewhere around here, between 270 and 365 degrees. And this is the line. So, and that's how to do your polar plot. So you can see that, of course, this is your R, right? This is your R. And then this is how that translates here, which is equal to 2.24. And then the angle is 296.57. And this angle now, this tiny angle now, is the minus 63.43 we got at first. Okay. So in conclusion, you can see that it is so interesting that polar form provides a useful representation for complex numbers, and it simplifies certain operations and graphical interpretation. So you may not get the full import of this until I do the next video, where I show how we can use how we do addition, subtraction, multiplication, and division in polar forms. All right. So understanding both rectangular and polar forms is essential in complex analysis, because each form is useful. Each form is useful in certain situations. So you should know when each one will be useful, and then apply it as expected. So as usual, I have some practice questions for you. So you want to convert from one form to another. Convert 3 plus 4i into polar form. That's in rectangular form. Convert into polar form. Then this one, this is in polar form now. 2e raised by I 30 degrees, and z2 equals 3e raised by I 60 degrees. That's polar form. You want to convert it into rectangular form. And of course, you want to convert this rectangular minus 3 minus 7i and W2, which is 7 plus 3i, into polar form again. And lastly, you want to convert this polar form, 5 cos 45 degrees plus I sine 45 degrees, into rectangular form. And that's how it's been in this video. If you have not signed up, if you are not subscribed to this channel, please do that, and then hit the notification bell so you don't miss other juicy videos that are coming your way. Thank you so much for listening. See you in the next video.